So for our science fair project, we have made an ROV, remotely operated vehicle, called the SUV, Submersible Unmanned Vehicle. What it's supposed to do is go underwater and cruise around, showing us videos of anything underwater.
So we don't actually have it finished, probably as you can see here. It's going to be controlled by this control box. It has switches in. Whoop. It has switches. Darn it! It has switches that we've wired them up by that, but they will be connected to this radio wire, which will go to this engine, and the two other ones we have over here. One of them doesn't have a propeller on it, but they're going to go back here, and that's going to allow us to turn the SUV and drive forward and backward. We're going to mount a camera up here if we can, and put a hopefully ballast tank, maybe just a float, here and here. This would be an end cap to one of them. And we do hope to carry this project into next summer and possibly the next science fair.
So basically, that's it. And this will have like 3 of these connected up, one for each engine. You just put it on, connect the wires, and it starts to go.
Here.
Can't do that.
You can look at the propeller here.
This engine allows us to go up and down.
So it would be actually mounted like that.
This one will allow us to go up and down. Our other engines go right here, allowing us to turn and go forward.
Yeah.
And this is a 3D printed holder, which connects it straight into the PVC pipe.
Yeah.
Just bolted in.
Actually, I can demonstrate for right now. We can actually right now here we can spin the propeller for you. We can drive the engine. So this would usually be going underwater. Allowing us to bring this up to the surface. It would be up like that, but up to the surface and down closer to the bottoms where we could take videos.
Hi, my project was electric lemons, and I made them so the copper goes to the nail, so it's positive to negative like in a battery, and then it just makes the light up on the paper. And I have fun facts and my conclusion, my hypothesis, materials, and a list of words.
So my project's on the effects of modulating height above average terrain at different heights and distances on radio signal strength and quality. My name is Sanjay Grindavajan, and I'm here to present to you my science fair project. And the question I asked was basically, when modulating height of average terrain, and modulating is basically when you basically change signal. Like, it's not like when you transmit something on like the radio you listen to in your car. It's not like you're immediately going to just like get the signal just because you said something. You have to modulate it. It's based on, and there's machines that can convert voice into into modulation. And there's different ways of modulating by changing the signal. To modulate in short means to change, and so I invented a new way that involves moving the radio up and down to adjust signal strength, like when your radio is static and when it's not. So the question is, how much do we have to move the radio up and down to get a clear signal so you can understand what the person's saying? For example, if you're listening to your FM radio. And the purpose was to develop this modulation so it might be able to replace the radios in your car and maybe even the internet entirely. And I hypothesized that if we use these two radios that are tangled up in the rope right now, to find the best height. The best height would be between 10 and 12 feet. Because last year, when we tested just to see if it worked, using a constant of around 8 feet, it wasn't enough. So I think that just a teensy bit more, 10 to 12 feet would be enough. And this, so variables included the independent variables, which is modulation height, which is, for example, if I'm to take a radio right now, I use this and move it up like this. You see, up and down. And how high should I do that? And distance of transmitter would be like moving these two-way radios farther apart, which will, a signal goes out of range on standard radio. This modulations would sound pretty similar, so you can relate to that. And the dependent variable is the signal strength, which affects how static, the amount of static you hear when you're listening to this radio station that's far away. Materials include my radios, my rope, the duct tape on the rope, the duct tape on the transmitter, the measuring tape that found out where to put the duct tape, and the procedure, steps 1 through 4, is all this setup. Setting up this little contraption here. And wait, power just went out? I didn't realize. And well, so right. Anyway, so parts 5. So the rest of the steps is going to involve me and my helpers going to the locations. Me and one helper and I both went to Site 1, and my other helper went to the balcony to modulate the radio. Oh, there's machines that we didn't use machines. We just had to modulate it by hand using other rope contraption. And well, so. Oh, anyway, so when we asked for the control, which was by moving the radio down down all the way to the bottom, and then recording the signal strength there at location A. When you turn the radio on, you have a signal strength indicator, and well, so that indicator would recognize the signal strength, and that we used to record it, and then if we will move to the next height, and so on until we reach the top height, and then we moved to another location, and we tested this on 3 different days with 4 locations, and well, so the graph shows that, as you can see, 11.2 feet, which is ironically equal to 11 foot 2, and had mostly a clear signal strength throughout the whole thing. So that's why I think that was the number one, and it happened because, well, that's the only one that's actually more than the arms reach away. Like, you can reach, this is each up to 7'4", just like this high. And how 11 foot would be way up high, which is why we had to use the balcony. And 14'8" would work, but anything above 11 foot too would work. So my hypothesis of 10 to 12 feet was correct. And thanks for listening to my project. And acknowledgements to my mother, Dr. Vindarajan, my sister, Tara Vindarajan. My mother was the moderator. My sister helped record a notebook on day 1. And my mother's friend, Dana Yerger, helped record on days 2 and 3.
So basically what I did is I did how to generate an electrical current from your fingers. So the reason that I did this is because it sounded cool, and also to learn the dark side of the Force, because in Star Wars the Sith used Sith lightning, and so yeah. And then also to create electricity to zap things. That didn't really happen. The equipment I needed to use was an aluminum pie plate, a metal thumbtack, a pencil, a black box with handholds and a window, a wool sock, and styrofoam. The steps to making the project is put the thumbtack face up in the center of the plate. Put the eraser into the sharp point of the thumbtack. Rub the black sock on the styrofoam for more than 10 seconds. Put pie plate on the styrofoam, holding it by the pencil. Place the box over that little sculpture you made. And now my results on what caused the shock is caused by a negative charge built up by rubbing the sock on the styrofoam. Your finger has a positive charge, so they react in the form of electricity. Now, the way that you connect that is you put your hand through the handholds, and then you put one finger next to the pie plate, which is right now in there, and then you'll feel a shock. And it works, just I thought that there would be a little bit more zap to it, and in the future I might want to find ways to increase the positive charge in your fingers, because there's enough negative charge in the styrofoam that it's just all relying on your positive charge. So you would just put it in there, put it right next to the styrofoam, and you should feel a shock in there.
Hi, I'm Katie. Hi, my name is Sarah. This is our science project. I just forgot what that was called. And it's about how little light does a plant need to grow, as it says right here. And we added a bunch of colors because we decided not to make it too bland like other people. No offense, other people. And so our hypothesis is a plant will need a lot of light to grow. And these are the plants. And these are the ones that were in the closet. Right here.
We got this at Shaw's, and we found this in the closet.
And these are the procedures. And then the conclusion is the plant that was in the sunlight grew faster than the one not in the sunlight. That sounded better when we typed it, but whatever. Plants need water, sunlight, and dirt to grow. And what do we have left? Oh, the materials were 3 basil plants, closet space. There's no closet here. 2 lights. There was the light in the closet. No, not in the closet. Sunlight and water. These are the ones that were in the closet. These are the ones that weren't.
So this is the conclusion that our teacher helped with us, like at school or something like that.
The background research is photosynthesis is what they call it when light affects plant growth. That is what helps it grow straight and tall. I'm not even holding this one up. Oh, wait, didn't we just say the conclusion? Oh, well, the results are that the plant that had light lasted longer than the plant in the closet, and the plant in the closet started to die, and it looked like it was sad, and the plant in the sunlight looked like it was growing, and it stayed growing until the sun set, or until, I don't know, it just says until they didn't have a sun. And then the sun came out again and the plant had enough food to start growing again.
My project is about the hydraulic and electric systems. One most common is the hydraulic dams because they help stop rushing waters and waves and currents from the rivers or oceans. And they're also going to produce a lot of amount of electricity to its area that is not non-toxicated good, that is good, and that may be a case that could stop global warming. And another familiar one is the hydraulic bridges, which the most familiar ones are the self-lifting, because without their electricity, they can't. Without the electricity, they're not able to lift and stuff, and they won't let the boats to pass. So they need that electricity to produce that strong amount of metal. And another one is the network arch bridge, which I don't think a lot of people are familiar of, but it's a really interesting thing to learn about because over here in the model, you can see that there are network cables, the ones that look like X's. They're supposed to produce some electricity to the electric towers. If it doesn't have electric towers, then it will just produce electricity for the road deck itself, so that it can produce enough electricity for the road deck to be safe for traffic to go on the bridge. And hydraulic buildings, stations, and warehouses can be familiar of that because warehouses need their electricity for importing and exporting, and without it, they can't import and export without their strong electricity, of course, like the others. And the stations, they need a lot of electricity for that. Some people think they only use like coal or any other electricity, but they can also use hydraulic electricities. They need all that electricity for the subway trains, buses, and other movement and stationary vehicles. And the purpose of this is that people need this because it could be a case to stop global warming, and it will be able to help other communities and help other residential zones for their electricity without having to use oil or gas. And for the project, I used similar to the network arch bridge. I would use my iPad an iPad Air for the road deck holder, and I used 2 cups, more like maybe 6 to 31-inch cup would be good, and I used that to hold the iPad so it can look like it's just like a bridge, and we'll actually need that for uses like using the toy cars as like the traffic on it, if you want to do that, or using heavy rocks to do it. I think that's a good idea. But if the iPad is on 0%, that will mean the traffic on the project will be unsafe, and traffic is not going to run smoothly at all. But if the project was if the project of the iPad itself was 100% charged, then the traffic on it, rocks or toy cars, all of that traffic will be safe. Just like on this bridge over here, it needed electricity for the traffic to run smoothly, and nothing could make the bridge collapse. So yeah, the lower the iPad is charged, the more likely the bridge is going to collapse. So that was my project today. Yeah, hope you enjoyed it, and thank you.
My science fair was called Pink, Blue, or In Between. The question I wanted to answer was whether females are attracted to pink, the color that has been marketed to them mainly, or other colors, and the same for males but with blue. My hypothesis was that if I give a large group of boys and girls 2 surveys and ask them to pick objects that most appeal to them, then girls would overall choose pink objects and boys would overall choose blue objects, because those colors have been marketed to them for approximately 12 to 13 years. My controlled variables were my female test subjects, my male test subjects, survey number 1 and survey number 2. My dependent variable was the responses to the surveys I received, and my independent variable was the questions I asked in the surveys. For my materials, I used my team at Lawrence School as the sample group, and I had these 2 tests with objects that were different colors to see which was chose most often. So I received the results and I converted them into percents, and I found that my hypothesis was proven wrong because most girls actually chose colors other than pink, and most boys chose colors other than blue in both surveys. I think this happened because lots of people always want to fight against the social norm, and they don't want to be girly girls or boyish boys, and so they try to find colors for themselves that are just their colors. And some things I could do differently was I had some trouble with people answering questions dishonestly and saying they were boys when they were girls and they were girls when they were boys, and I had some problems with the data, but other than that the experiment went pretty smoothly, so my hypothesis was proven wrong, and girls like colors other than pink and boys like other colors than blue.
So our science project was on the science of spotting. Dancers always turn and spot a point so that they don't get dizzy and they stay balanced. So we were asking the question, because we are always told to spot at eye level, what would happen if we spot lower or higher than that? So we thought that eye level would be great because we trust our teachers and it's easy to find. So we laid down a cotton tape on the floor and turned, and our partner tracked our position with sticky notes, and then our results came as follows, and they were very inconsistent. However, we did find a few trends. So for Bethany, my partner, it was best way lower and way higher than eye level, and for me it was eye level and higher. So it wasn't very consistent data, but I think it would be helpful for the future, so I know how to spot at different points. And some things we could do differently next time would be trying higher spots, because we could only reach 8 feet, and trying more advanced dancers, because they wouldn't have to worry as much about technique.
Our project for the science fair is skee ball, and how you play is we have a tennis ball, and you have to roll it up, and this one counts as 10 points, this one counts as 50, and this one counts as 100. And the more points you get, the more slime you get. And we also have other friends coming, and they have the flashcards for questions. So if you do 1 problem, you get 1 roll. 2 problems, you get 2 rolls. For 3 problems, you get 3. No, wait, I did that wrong. Would you like to say something?
So 2 problems you get 3 rolls, 3 problems you get 4 rolls, and then 1 problem you get 2 rolls.
Hello, my name is Grayson. My project is called Spunky Sprouts. My question was, Which seed will germinate first? Will they all be the same height? I tested this by planting lettuce, spinach, basil, dill, and parsley. I learned that a seed gets to the ground and grows into a little plant from inside the seed. Needed soil, water, plant tray, and a light that was on 24 hours. I measured the height each day.
Keep going.
I predicted the seeds will grow in this order: dill, sweet basil, and lemon basil, spinach, lettuce, parsley. I looked at the packages for the predicted number of days. I looked at the seeds in my microscope. I found out that spinach and lettuce started fastest and dill started later. It grew fast. The spinach looked bigger because of leaves. Show graph, pictures, plants. Thank you for listening.
What? All right. So our project is named Cassiopeia. It's like a throwing ball game, and like you throw it in the holes, and whatever you can only put the ball. You can only put the ball in the hole once, and you grab the meteorites and you throw it in, and what you learn a fact while you're throwing them in, and yeah.
Me and my group did foosball. So each player has a number on their shirt. So each player has a number on their shirt, and if you have 2 points if you have 2 points and you score with number 1, you multiply 2 times 1, and that's how you get points.
First, you pick a number from 1 to 10. If the number is even, then you use side B. If the number is odd, then you use side A. Then spin the handle on the side you got, the number of times that your number is, and solve the math problem, and then solve the math problem on the whiteboard. If it takes you 15 seconds or under, you get 3 prizes. If you finish it in 16 to 30 seconds, you get 2 prizes. And if you finish in between 31 seconds and 60 seconds, you get one prize. If it takes longer, you lose.
All right, this is the project that my teammates and I made. It's a version of Down the Clown, but with math facts. So you'll choose easy, medium, or hard, and you'll take the easy, medium, or hard blocks. This is a hard block. It has the answer on it, 266, and then you'll look at one of the math problems up here and try and find which answer matches the math problem, and if you get it, if it falls down and you get it, then you get it right. But that wasn't the right one. I don't know how to do these math problems. No. I'd like to thank my mom, my dad, my grandmother, my grandfather, my food, my refrigerator, my food, my dog. That's it.
We were engineering for earthquake buildings. There's libraries and hospitals and different houses and apartment buildings where we had to make it stand up and at least it not fall down, and at least a 7 on the Richter scale. And then we could we had to make it look like different things in a certain height.
My project is about tortoiseshell cats and their reflex time compared to the long-legged fly, which has the fastest reflex time in the world. And their reflex time is 17 milliseconds, and my cat's time I measured is 33 milliseconds. And the tortoiseshell cat, it has a faster reflex time to the average cat, which is 50 to 70 milliseconds, because they have higher energy levels and tortitude.
So basically, my project is we're testing out 3 different paper airplanes. We're testing out 3 different paper airplanes, and airplane 1 is this airplane, and we want to see which direction like the wind is going after it hits the airplane, or like what's the stability. And so basically the air comes through here and sucks the airplane in, and you press it like that, and the air stabilizes it, and like this kind of, yeah, like that. And then you put strings through the airplane, and you can see which direction the air is going from the strings. And airplane 1, it was pretty stable, like right now, and most of the strings went below the wings. And airplane 2, most of the strings went through the strings. And airplane 3, it didn't fly at all. And the first paper airplane went 18 feet, the second paper airplane went 15 feet, and the third paper airplane went 9 feet. So the stability probably, and we threw the paper airplane, and airplane 1 was off aim, kind of. Airplane 2 was really on aim, and airplane 3 didn't fly. So the stability probably affects the aim, and the string direction probably affects the flight of the paper airplane. So most strings that, if the paper strings are down, it usually means that it's going to fly well.
Whenever you're ready.
Okay. My science project was, can the color of your house reduce your energy footprint? The project was to see if the color of the outside of your house could change the temperature inside of your house. My hypothesis was that box 3, the brown box, would be the warmest, box 1, the white box, would be the coldest, and box 2, the yellow box, would be in between box 1 and box 2. The way I did it, the materials I needed were 3 of the same size shoe boxes, white, brown, and yellow paint, paintbrushes, 4 thermometers in Fahrenheit, 1 large tray, 1 heat lamp, ice, salt, a plastic bag, and a lab notebook to record your data. The way I did my project was I painted one of my boxes white, 1 brown, and 1 yellow. So from that, the yellow box was box 2, the white box was box 1, and the brown box was box 3. After that, I recorded how hot it was inside the room. It was about 70 degrees Fahrenheit, and then I recorded the temperature inside the boxes. And that's on the graph right here. And then I made an ice tray by putting ice cubes on a tray, adding salt, and putting it in a bag so that the boxes didn't get wet, and I left that on for an hour. After I did that, I took it off and recorded the temperature inside, and that's on the graph right here. And then I put a heat lamp on, which is about 200 degrees Fahrenheit, and I left it on for an hour, and then I recorded the temperature inside the boxes. I did that 4 more times to have a total of 5 tests. After I did that, I made the graphs I needed and averaged out the results. The results were box 3 was the warmest, and box 1 and 2 were similar in temperature. When the boxes were at room temperature, the average temperatures were box 3 was at 68.8 degrees, box 1 was 67.8 degrees, and box 2 was 62.2 degrees. When the boxes were cooled, then the average temperatures were box 3 was 61.2 degrees, box 1 was 59.8 degrees, and box 2 was 56.6 degrees. When the boxes were warmed, then the average temperatures were box 3 was 68 degrees, box 1 was 66.2 degrees, and box 2 was 66.8 degrees. In conclusion, box 3, the brown box, was the warmest, while box 1, the white box, and box 2, the yellow box, were both cold. The goal of the project, or how it could relate to real life, is to see if your house is warmer or colder depending on the house color. So you could save money and electricity. And with all that money you are saving, you could up your allowance or even start one. The problem with my project was that the boxes were very thick. Maybe if the boxes were thinner, they would have changed more. But in the end, my hypothesis was half correct. Box 3 was the warmest, but the other boxes, the yellow and white boxes, were not much different from each other.
First, we went out and got a bunch of gum, and we got 2 timers, one for my brother and one for me, and we put the gum in our mouth and started the timer. When the gum was out of flavor, we would stop the timer, and then we would put it on the results and see what, and when all the gum was finished, we would put it all on the main paper. But the first, we did 2 rounds of gum, and the first time we did it, me and my brother did it together, and the second time we split up into different rooms. So the second time we got a lot different answers. So the second time was the main results, because we thought that one was much better results, and it's mostly it.
My project is the dancing pepper, and it's about how pepper can move away from soap once the soap touches the pepper. And
so our project was what a successful circuit would look like, and we made a circuit with wires and copper tape. They both worked, but we had nuts and bolts.
We tried all different things like Play-Doh, paper clips, and like magnet. We tested them to see if they worked, and the magnet and the styrofoam did not work, and the paper clips, the potato, and the Play-Doh did work.
Anything else, guys? My project is called How to Make a Guitar Sing. The purpose was to see the frequencies of each guitar sing, to see which one had the most frequency in decibels. My hypothesis was that the lowest strings, E and B, would have the highest decibels since they're lowest on the guitar and they're the thinnest. But to my surprise, the D string, which is semi in the middle of all 6 strings, had the highest of 68.9 decibels. And the E and B string only had 64 and 61 decibels.
Perfect, ready to go.
Okay, so we made a circuit, and it's closed so the electricity can get through. And if you press this, it can turn on the fan and the light. And we made a poster to see what happened and didn't happen. If you take one of these pieces away and put a screw, you can make it work. Well, it used to work.
That's okay.
And this was the only thing that did work for our circuit.
Anything else?
No.
And whenever you're ready.
Okay, so my science project is about fruit power battery, like to see which fruits contain electricity to light up an LED light. It was to find out which fruits contain electricity. So you gotta use zinc nails and copper pennies to light up the light. So so it was only the zinc nails to light up the light, not regular nails. And you could use lemons. The more lemons you have, the more electricity you get. Yeah.
This is my science fair project. My question was, how many cars can fit on the track before they crash? My hypothesis was 6 cars. But I was wrong. As high as they can go is 10. But there were also other experiments like 3, 1, or 2. My method was put together the track, then turn the track on, then put cars on it. I have a few pictures that can show you what they look like. This is how you see them crash, and look at them racing. This is my model. There, it tells you how many they got.
And can we get a demonstration?
This is what they look like when they're racing. Alright. Hi, my project is called Girl Scout Cookies Sales versus Likes. So my question and my hypothesis was would my sales and my survey be the same? I had to go through a lot of steps to get to that point. I had to decide how many boxes I was going to sell of each kind. Then I had to talk to the Shaw's manager so I could sell cookies, and that's what I did. And I had to also take a survey of what people liked. After that, I had to organize my data with math. So you see, there was a big difference. Friends, so my results were false, as you see on my raw data. My process data shows a little better, though. So my conclusion was that Thin Mints are definitely the favorite, because my process data shows they have the highest percentage. And my hypothesis was right for the lemonades, because on my process data they are both 5.5%. And then the strangest thing is that peanut butter patties sold better than Caramel Delights, when Caramel Delights are known as the second favorite Girl Scout cookie. Yeah, I thought it was really strange too. And if you're over here, I'm selling Girl Scout cookies.
I did my science project on rusting metals. I named it Bust the Rust, and it was about having 3 different types of metals and putting them in lemon juice. And I put them in lemon juice for 2 months, and after they all got rusted, and my hypothesis was that the steel was going to rust the most. And this one is the steel. this is aluminum and this is iron, and my hypothesis was correct, and my hypothesis, no, it was correct. So the steel rusted all the way, and it actually turned completely black. This is what it looked like before, but with the aluminum, it didn't rust it; it just ate at it. Lemon juice has a 14.4 ppm of dilution, so instead of rusting it, it actually just ate at it and made it look disintegrated. It still rusted it, but not as much as it should. And this is what it looked like before, and it's just a normal piece of aluminum. And then the iron, actually, it rusted, but not as much as what you would think. It only rusted about 30%. The steel rusted about 100%, and the aluminum only rusted 40%. And then, so the reason I did my project is because I like to work on cars and everything. So when people make cars, you would wonder what they made cars out of. And so you would think, what should I make a car out of? You're not going to make it out of aluminum, because if acid gets on it, it's actually just going to crumble. So you would probably make it out of steel or iron or something like that.
Whenever you're ready.
So I did my project on, it's called Memory by Movement, and my experimental question was, does movement promote memory? And so my hypothesis was, if a person paces while memorizing a set of numbers, then that person will be able to remember more the numbers, because movement is stimulating to the brain. And so the way I did it was I read a list of 8 numbers to a person standing in front of me, and then I would have them recite back as many as they could. And then I would repeat that, but have them pacing back and forth. And so my results were that 2 out of the 3 subjects could remember more when pacing, and so it proves that movement does promote memory. And so during my research, I found out that when we move, it stimulates our brain, and the stimulation causes the information that we learn to move into the memory section of our brain. Also, when we move, it increases blood flow, and blood flow allows oxygen into our brains, and our brains need oxygen, so when it gets more, we can think better and we can remember more.
So my project was effects of temperature on energy production in a community of anoxic bacteria present in sediments. So basically my question that I was asking is, if you change the temperature of the environments that certain bacteria are exposed to, the bacteria that don't use oxygen to live, how would this affect their production of energy when hooked up to a microbial fuel cell that I have here? So my hypothesis was that the sediments and the samples in the highest temperature would have the most energy production. So that was 37 degrees Celsius, which is about 98.6, which is your body temperature. The samples that would do the second best would be in 27 degree incubators, 27 degrees Celsius, so that's about 80 degrees Fahrenheit. And the worst energy producing samples would be outside as a control, which I found the average to be about 33 degrees Fahrenheit. What I used here to build the microbial fuel cell is basically 2 1-gallon containers. You need to construct a salt rope here, which is basically a cotton rope soaked in a really, really saturated salt water. This makes the electrons flow from one container to the other, and make sure that you can see how much energy is actually going through this multimeter here, which will be set to volts. All my measurements were done in volts. These copper wires here that connect to the multimeter, which is connected to this mesh here. So that shows how much energy the samples are producing in this container right here. So what I did is I went to Sippawisset Marsh. I collected nine containers here, 9 1-gallon containers of the sludge, which contains my bacteria, and and I put them into these containers. We run at a Hui lab. We ran 1 minute each, 3 times, so you could see it better on a chart. There's more data there. So my results from this after 6 trials over 21 days, 3 weeks, I found the best working samples were actually in the 27 degrees Celsius incubator, which is about 80 degrees again. The second best producing samples by a small margin were the control samples, which were subject to the outside temperatures and conditions. And actually the worst samples were the 37 degrees Celsius samples, which was a surprise to me because it rejected my hypothesis that those would be the best. I based my hypothesis on the fact that at higher temperatures, molecules move faster, and I thought this would mean that since the bacteria are moving more, that their metabolic processes would be faster, and they would be able to produce more energy. But it turns out that maybe this was too high of a temperature for these bacteria, because Sipawissat Marsh, the water temperature is not likely to reach 98 degrees in any point of the year, let alone winter. And so this was a bit of a surprise to me, but it showed me that bacteria basically have a limit to how high and how low they can produce energy. And it makes sense to me that the 27 degrees Celsius samples would have been the best because it was a better fitting temperature for them that they might have seen.
Hi, my name's Gavin, and I'm doing an experiment on blubber. Blubber is fat that polar bears develop when they're getting older. And this is a picture of a baby polar bear, a baby sea lion, baby beluga whale, and a baby seal. My hypothesis was if I put Crisco on my finger, then it would stay warm because it's insulated like blubber. Blubber is fat, and my problem was most Arctic animals live in a very cold habitat and need blubber so they can survive in the cold water. My materials were cold water, ice cubes, 2 bowls, stopwatch, Crisco, and a thermometer. And my results were the finger with blubber on it could leave in there for the rest of the day. And blubber keeps them warm in cold water so then they can swim. And my test scores were 43 degrees, 41.6 degrees, 40 degrees, 39.5 degrees, and 40.3 degrees. My finger with blubber was 17 minutes, 19 minutes and 24 seconds, 11 minutes and 2 seconds, 30 minutes and 46 seconds, and 12 minutes and 2 seconds. The finger without blubber was 17 minutes, 4 minutes and 15 seconds, 11 minutes and 2 seconds, 1 minute and 12 seconds, and 12 minutes and 2 seconds. And I got this idea from Science Buddies. They helped me a lot with my science projects.
My project was on eutrophication, which is when pollutants such as fertilizers go through into the groundwater and then go into freshwater ecosystems, including estuaries, which causes algae blooms, which means that the algae that live in the fresh water grow and grow and grow. And they make a top layer which stops the sunlight from coming through and also uses up all the oxygen, which basically kills all the other organisms living in that ecosystem. And I've written how we can control it using different methods. This is an interactive piece that you can test your knowledge on eutrophication. And this is a list of pollutants, including organic substance, toxic substances, thermal pollution, and ecological pollution. And it's just basically an information thing for anybody who would like to know how this kind of thing works.
Galvanic corrosion is when 2 different metals that are joined together come in consistent contact with an electrolyte like water. When immersed in the base of metal with lesser nobility, will undergo corrosion.
My hypothesis is that when the metals are touching and put underwater, some will have visible corrosion and the others will not have any. The reason why I did this project is I thought it was very cool how different metals have different reactions with one another. I think it's a very good thing to know and a thing that you should learn. The requirements for galvanic corrosion is 2 different metals corrosion potentials, direct to metal contact, electrical contact, and a conductive electrolyte solution. An example is salt water. The metals I used are, the plates are aluminum, bronze, carbon fiber, which is graphite, copper, stainless steel, and steel. The rods I used were aluminum, brass, silicone, bronze, mild steel, copper, and stainless steel. The additional materials are plastic bowls to contain the metal, water from West Falmouth Harbor, plastic bins to store the bowls, a Sharpie for labeling the bowls and the baggies, tools to cut the metal, tools to tap the metal into plates, a phone to document the progress. And then here are the images of us tapping it and cutting it. And we ordered the materials, stored the materials, and cut them into pieces. We tapped each rod into one another and photographed each sample. The methods we did were, we filled each bowl with salt water from West Falmouth Harbor, placed one plate, we placed each set of metals in the bowl, and clearly labeled each one with the correct materials. We placed them outside on my covered porch, and let each metal sit in water for 30 days and documented it on my computer. When two metals are further apart in the list of driving force for galvanic corrosion or nobility, there is a chart for it. And when they're farther apart, one at the bottom and one at the top, the zinc, which is one of the lowest, zinc is one of the lowest, and graphite is one of the highest, and when they're mixed together, there would be a very, very bad reaction. And here is the graph for it. So this is the lowest, which is the worst, and these are the highest. Which this graph is incorrect because graphite's the highest. And here are some of the results. I noticed that when different metal were together, some were affected and the others were not. The levels of each metal corrosion was very different throughout my work. And then here's my graph for the plates and the reactions. And here's my graph for the rods are the red and the blue are the plates. And I did it by visual to see which one was good, which was worse. And this is one of the metals, this is what steel and bronze looks like. But it wore away, annoyingly. And then here are the steel plates on day 1, and these are day 2. These are the 23rd, which would make it about 30 days. And here is this versus this, and they were very different. It's because when the plate which has the bigger mass is mixed with a smaller mass metal, the one with the bigger mass isn't going to be as affected as the one with the smaller mass. Here are the bronze plates on day 1, and here are them on 221. This is what happened. And then this is this, and there's a ring, which it's not seized, but it's not good. And here's aluminum, pure aluminum, right here, and then this is aluminum steel. This is a carbon plate with bronze and bronze plate with bronze rod. And then there was, in the 1990s, there was a problem with the Statue of Liberty because it was made out of iron and it was wrapped in a copper, or had iron supports, and it was wrapped in a copper skin. And when iron and copper are mixed together, it is not a very good reaction. And here's a story about the Big Dip, how light fixtures were falling down because of poorly designed thing. And there's zinc on on an engine because it's a stainless steel rod and a bronze propeller, and when they're mixed together, they would normally corrode. But when there's zinc, it doesn't corrode because zinc is a sacrificial metal, so it will disintegrate itself and the others will not be affected. And then here's just the outcome. In conclusion, the metals on the nobility chart had different ranges, and ones were good and the others were not. And then I thought it was a very fun project, but also it took a very long time to get the reactions or the results, and I think everyone should know about it. And here's my works cited.
Okay, so my question for my science project was, which melts ice faster, Crazy Jane's mixed up salt or iodized salt? And the Crazy Jane's mixed up salt is just salt with cooking seasonings in it. And then my hypothesis was, if salt is added to melt ice, then iodized salt will melt the ice faster, because 1/2 tablespoon of iodized salt will be comprised of more salt than 1/2 teaspoon of Crazy Jane's mixed up salt, because Crazy Jane's mixed up salt has the seasonings in it, and so there's obviously going to be less. And so what I did was I took 15 ice cubes and put them in 3 bowls with 5 in each bowl. Then I spread 1/2 teaspoon of iodized salt on one bowl, then the same amount of Crazy Jane's mixed up salt over a different bowl, leaving one bowl untouched. I then set a timer and timed the ice cubes until each bowl was completely liquid, and then I repeated this process twice more for 3 trials. And so my results ended up being that Crazy Jane's mixed up salt the first trial took 1 hour, 37 minutes, and 4 seconds. Then the second trial took 1 hour, 50 minutes, and 50 seconds. Then the third trial took 1 hour, 44 minutes, and no seconds. Then iodized salt took 1 hour, 30 minutes, and 34 seconds for the first trial, 1 hour, 42 minutes, and 6 seconds, 1 hour, 20, and then 1 hour, 21 minutes, and 37 seconds. Then no salt took 2 hours, 11 minutes, and 30 seconds, 2 hours, 4 minutes, and 2 seconds, and then 2 hours, 5 minutes, and 19 seconds. And so it ended up being, as you can see here, this is my graph. My results did end up matching my hypothesis. However, I did expect there to be more of a time gap between the iodized salt and the crazy salt, but they ended up on average only being about 12 minutes off of each other. I had expected them to be maybe about 30 minutes apart. And then the part of my experiment that went the best was the distribution of salt. When I put the salt on the ice, it was always exactly 1/2 teaspoon. If I were to repeat this experiment, I would have 3 separate timers, 1 for each bowl. This way it would be easier to get through all the trials and even do more than the amount of trials that I did. And then in this experiment, the independent variable was the type of salt that was being used. The dependent variable was how long it took for the ice to melt. And then the constantly controlled variables were the ice cubes were all the same size, the ice cubes were all tap water, the ice cubes were all placed in the same bowl type, there was no direct light shining on the ice, and only 1/2 teaspoon of salt was added for each trial, and then the bowls have no human or animal contact. And so, as I said before, I measured them with a timer, and I timed how long it took for each bowl to fully melt. And then the mechanism behind this all was chemistry. The chemistry was that the ice and water are in a dynamic equilibrium with each other. This balance, however, is easily upset, and adding salt can throw off the equilibrium. When salt is added to the ice, the total number of waters captured by the ice per second goes down, and so does the rate of freezing. The rate of melting, however, is unchanged, so the melting occurs faster than the freezing. And then a couple of vocab words. Dynamic equilibrium, when 2 opposing processes are occurring at precisely the same rate. Freezing point, the temperature at which a liquid turns to a solid when cooled. Iodine, the chemical element of atomic number 53, a non-metallic element forming black crystals in a violet vapor. Melt, make or become liquefied by heat. And then salt, an ionic compound that can be formed by the neutralism reaction of an acid and a base. Then there are also a couple of facts that went along with this project. Fact 1. An ice cube placed in a warm room is the system, and the warm room plus everything in it are the surroundings. The ice cube absorbs the heat from its surroundings and melts. Fact 2. In changes of state that happen because of heat, such as an ice cube melting, the temperature will remain constant. Fact 3. Salt occurs in many parts of the world as a mineral. It has been mined for thousands of years. Fact 4. Sea salt and salt as a mineral are chemically the same but gastronomically different, so they're different for cooking. Fact 5. Salt alone cannot melt ice. There must be a sort of water involved that will start the melting process. It is fortunate that snow and ice are usually covered by a thin film of water. And then, finally, my sources for the project were AntoineFrostberg.edu, Kistner.com, Malden Salt, and a Prentice Hall chemistry textbook.
Okay. My project is tempering chocolate. My question was, when testing chocolate under different temperatures, will it change its shape, taste, and how it breaks? And my hypothesis was, if I change the melting points of chocolate, then I predict that it'll have the same taste, but it may be oddly shaped and it may break in different ways. Some background facts for this project were some people actually don't consider white chocolate to be chocolate because it has different oils and a different kind of cocoa butter. Also, this one most people know, milk chocolate and dark chocolate are very much the same, except the fact that dark chocolate doesn't have milk and milk chocolate does. All chocolate is supposed to have a specific taste, sheen, and smell, and if it doesn't have that, that's one way you know that it's been made wrong and it's not good chocolate. Tempering is a process in which the cocoa butter and chocolate is hardened into a specific crystalline pattern. When the cocoa butter molecules are in this pattern, the chocolate is shiny and breaks with a sharp snap. That's also another way to know. If it's very hard to break, then it's not good chocolate. Some background vocab is tempering. Tempering is the process that re-establishes the cocoa butter crystals that are in real chocolate versus compound chocolate. Melting point is the temperature at which a given solid will melt, and a freezing point is the temperature at which a liquid turns into a solid when cooled. Temperature, the degree or intensity of heat present in a substance or object, especially as expressed according to a comparative scale and shown by a thermometer or perceived by touch. And a thermometer is an instrument for measuring and indicating temperature. My procedure for this experiment was using 3 kinds of chocolate. I tested all 3 kinds at 3 different levels or 3 different temperatures for 5 minutes each, and then I placed them in the refrigerator for 20 minutes. I measured this based on how the chocolate broke and looked when it came out, or how it basically reacted to the different temperatures. My materials were white chocolate, milk chocolate, dark chocolate, a chocolate mold, I just used a little flour mold, a thermometer, water, and pots and pans. My independent variable was the temperature at which the chocolate melts, and my dependent variable was the kind of chocolate. My control variable was also the taste of the chocolate. This is my table. I have all 3 kinds of chocolate at all 3 kinds of temperatures. What temperature they melted at and what temperature they froze at, and how some information kind of about them, like how they acted, how they came out to be, how they turned out. And here's some graphs of mine. My end why for this experiment was both the white chocolate and dark chocolate are much thinner than the milk chocolate because the milk chocolate has milk and is much more condensed than the other 2 chocolates. For example, milk chocolate 2, it was much harder to melt, and it didn't melt all the way because it was at a lower temperature and it had milk chocolate. So by the time I put it in the freezer, it was all lumpy and it came out in a weird way and broke in a weird way. My conclusion was, though the chocolate tasted the same, it did change shape sometimes, and it did break differently sometimes because of it. I think that one thing I could have improved on was less time in the freezer. I put the chocolate in the freezer for 20 minutes, and I think I should have done 10. I continued to check the chocolate while in the freezer, and even though it continued to change, by the time it came out at 20 minutes, it was all hard. But if I had taken it out at 10 minutes, you could have seen much more a lot more difference in the chocolate. So yeah.
This is the science of curling, factor friction. Yes, it is a pun. My question was, what type of curling broom goes the fastest? If you don't know what curling is, it's a Olympic sport that you play on the ice where you throw 42-pound curling stones, which look like this, which you throw on the ice and try to get it into a big circle. And curling brooms can really change that by about 9 feet. I wanted to see which one was the best, so I tested about 4 different brooms. Actually, 3 different brooms, but with one time not sweeping at all. We tested it by throwing the stones with this little thing right here. It can throw pretty consistently. Then we sweep them, same amount, put up a graph. And then my conclusion was the Lightspeed brand broom is the best because it's really light. It allows the sweeper to sweep the most and allows you to melt the ice faster, creating less friction and letting you keep your momentum longer, letting the stone travel about 9 feet more than without sweeping. And the science behind it is really momentum and friction, how friction slows down the stone when it's on the ice, and then momentum keeps it going. But the friction will slow up that momentum, so you have to sweep the ice, melting it away, and it will keep the momentum. And in curling, you can make a big difference with just sweeping. You can have about the difference between 1 foot and 2 feet can be the difference between losing a match and winning, just like in the Olympics. In the Olympics this year, curling, the curling team for USA won their first ever gold in curling. And that's pretty much the project. Some cool facts about curling are you used to sweep with normal brooms, which really didn't do much. They were kind of bad. Then eventually they switched to nylon brooms, which look like this, and they can melt away ice a lot faster, and they're a lot lighter. And I do this because I do curling with a bunch of my friends, and we've competed in tournaments around the world. One of my friends has gone to the national tournaments, and really just wanted to see what type of broom was really the best, and we got that, and it was a lot of fun doing it. And yeah.
So for our project, we titled it Controlling the Colors, and it's based off of the Stroop effect, which was discovered by John Ridley Stroop in 1935.
Our question was, which gender can solve the Stroop effect test the fastest?
And which age group could solve the Stroop effect test the fastest? The independent variable for which age group could solve the Stroop effect test the fastest was the age the different groups took, and the dependent variable was the time that each age group took to take the test.
The independent variable for question number 1 was the gender of different groups, and the dependent variable for question number 2 was the different times they took. Our hypothesis was if we test 15 boys and 15 girls using the Stroop effect test, that girls would solve the test the fastest because, according to Evolutionary by Charles Darwin, that girls' brains mature faster.
And we thought that if we tested 5 boys and 5 girls from each of the 3 different age groups, the age group of 10 to 18-year-olds would be able to solve the test the fastest because as you get older, your brain deteriorates, starting from early as age 30.
Our results were that girls did solve the test faster. They had a 13.38 average time, and the boys had a 14.68 average time.
Our results for question 2 were the 10 to 18-year-olds had a 12.08 as their average time. 12.84 was the 29 to 40-year-olds average time, and the 41 to 60-year-olds average time was 17.09.
So overall, both of our hypotheses were correct.
Just present it like I would judge.
So I wanted to figure out if I could make a magnetic motor. I wanted to figure out if I could make a magnetic motor that was more effective than an electric one. So I thought that it should work because it should just spin if I got it started, because if I arranged the magnets in the right way. But it didn't work, this one, because it would just get stuck. Because I couldn't make this thing flip over effectively, so it just got stuck there. So basically it didn't work, and I had lots of trouble with it because it didn't want to work either, because they were always sticking together. They do not want to come apart once you get together because the magnets are really strong. So
demonstration?
It doesn't really work, but it's stuck like that.
Awesome. So the magnets just propel it around?
Yeah.
Awesome.
I wanted to do something about psychology, so I decided to make up my own experiment and call it Phones, Attraction, or Distraction. My science teacher came up with that, so I've done a lot of research on how phones can distract you, and I've found out that having your phone around, like in your sights, can be very distracting and prohibit you from doing normal everyday things. And also, holding up your phone next to you can damage your brain, and it can lead to injury, like cancer. And you should really try to avoid your phone, like avoid being addicted to your phone, and just try to put it away a couple hours before bedtime and not check it once you wake up. So my question was, do people use their phones rather than their manners? And I predicted that the younger the participant was, the more likely it was that they'd be distracted by their phone. for my materials, I used a scientific notebook, a writing utensil, a participant who owns a phone, an assistant, and the assistant's phone. So first I would acquire my materials, and then I would take my participant into a room with no distractions and position my assistant outside of the door with their phone so that they could hear everything that was going on. Next, I'd start my survey, and I would ask them questions like, what's your favorite color? What's your favorite number? Things like that. And then on my Q question, which was, if you had $1 million, what would you do with it? I had my assistant text my participant, how's the experiment going? Then I would look to see if the participant checked to read their phone, or if they flinched, or if the ringer was on, things like that. And then I would continue my survey until I was done. And then afterwards I would tell the participant what happened. So I wouldn't tell what was going on before the participant started my science project because I didn't want anyone to be biased. So through my experiment, I've basically found out that my first generation, which is what I called my grandparents and them, are generally the least addicted to their phones. And then the younger generations get more addicted as they go on. So my parents' generation, they weren't addicted to their phones, but they definitely did have their phones closer to them. And then my generation, we definitely were addicted because some of us would look down and just detach from the conversation, and then some of us would read it. So I think that it definitely shows that my generation has learned to depend on technology when my grandparents' generation has grown up without advanced technology and learned to live without it.
Hi. Our project is Cleanish. We want to answer the questions, which household bacteria carries the most bacteria, and which cleaner, either Windex or method all-purpose cleaner, reduces the most surface bacteria. Our hypothesis was that the Windex would reduce the most surface bacteria due to its harsh chemicals, and that the wood floor would carry the most surface bacteria because of all the bacteria that your shoes carry in.
So our procedure was, first we taped off the area that you want to swab, and then you make it into two sections. So you make it like this, one side for method and one side for Windex, and then you take one of these swabs and you lightly dip it into water and swab both sides of the surface that you taped off. You transfer it into a petri dish, and then you lightly stroke it into into a star motion, but going outwards, so it disperses all the bacteria evenly, and you can see it grow in the right way. And then, so that's your control. You tape the petri dish shut, and then you do the same for all three surfaces 3 times for each. One with a spritz of Windex and one with a spritz of method, and then you wipe it with paper towel. Then you wait a week for it to grow after it's in a controlled environment, and you make a chart on a clear transparency sheet, and you say A1 is 25% filled with bacteria. You would record that, and you do the same for all 9 boxes, and then you record that into a chart and record it into a graph.
The materials we used were 2 small spray bottles, which are these. We used a clear transparency, a roll of painter's tape, markers, 18 petri dishes, 18 swabs, a bottle of Windex, and a bottle of method all-purpose cleaner.
So our control variables was the original sample without any spray, the petri dishes, the temperature of the room, and the size of the nozzle of the spray bottle.
The independent variable was the Windex and was the cleaner, so the Windex and the method all-purpose cleaner.
And then our dependent variable was the amount of bacteria found per square.
So we found facts about bacteria, and 5 of them are: bacteria are one of the simplest forms of life, being made up of only one cell. Bacteria occur in all different shapes and sizes: ball-shaped called spheres, rod-shaped, and spiral-shaped. There are medications that can kill bacteria, which are called antibiotics. Bacteria can live in food. Properly cooking food is a great way to kill off any bacteria that can live in it. Bacteria thrive where they can settle and stay. Places on which things can settle seem to have more kinds of life thriving on their surfaces.
So for additional background research, we decided to find on the websites each ingredient in both method and the organic or in Windex and the method all-purpose cleaner. And we also found their purposes. So a couple of the ingredients in Windex is water, which provides a liquid base, ammonium hydroxide, also known as ammonia, and that's a pH adjuster, and it alters with the stability of the product. And it also contains nitrogen, and nitrogen is what can help bacteria grow differently than just without any nitrogen. It also has sodium sulfonate, fragrance, and sky blue dye, which is not for just color, it's for knowing where you applied the product. And then method has water, again, for liquid base, sodium gluconate, which just helps cleaning metals and things like that, colorant and fragrance, as well as citric acid.
So as a result of our testings, we found that the most effective cleaner was Windex due to its harsh chemicals, mainly ammonia. Ammonia can kill Salmonella and E. coli. And we also found that the household surface that carries the most bacteria is the wood floor. This is because our shoes, 90% of the time, track in the bacteria to the transfer the bacteria from our shoes to the floor. Assuming that our trials were 100% accurate, both of our hypotheses were correct. And if we could change anything about our experiment, we would probably do maybe another trial and do another surface. So here are some of our before pictures. So this is us swiping it in a star motion, and you swipe the swab in a star motion, just so that makes it so you can see the bacteria more where it's spread out. And here's some active pictures. So these are different types of bacteria, because as I said in the 5 facts about bacteria, there are many shapes and sizes. So these could have been some of these types of bacteria.
And then when we analyzed the data, we found that on both trials, wood floor, untreated had the most bacteria, and Windex on both wood floor and the metal stool, and then on trial 2, the counter, reduced the amount of bacteria, while on all 3 trials, method, except for trial 1's wood floor, method didn't decrease the bacteria, but it didn't decrease it as much as Windex did. But on quartz counter and metal stool, both trials, method actually appears to have increased the bacteria, but when we did some research, we found out that it wasn't so much increasing it, but it was just dispersing it, because we wiped it evenly 5 times with a paper towel each side. But with the green cleaner, it's most effective when you use a rag or something harder than just a paper towel, and you are scrubbing it a lot harder, and that makes it reach as clean as it can get. So that explained to us why it seemed that method had made more bacteria. And we were surprised that the quartz counter was actually less than the wood floor, because as we were doing the project, we realized maybe the counter, which was near the kitchen sink, would have more bacteria. But it also is near the sink, so maybe water and dish soap were getting on it, making it cleaner just in general. And then the stool, we realized, would most likely have a lot less bacteria than the other 2 surfaces, because it's not a very, you don't track bacteria on there. Usually you're just sitting there. And yeah.
Hi, I'm Dario Palanza, and this is my project on cannon power. So basically, I decided to see how powerful a homemade combustion system could be. And so by doing that, I created a potato cannon, and I made a thing in front of it so I can measure how much force and how much acceleration the potato had. And then, so here I graphed the 2 force and acceleration of 6 different shots of the potato. And my hypothesis was that I expected it to be pretty powerful, but not anything that could hurt at it at all. And so after I did the whole setup and I did the experiment, I came to the conclusion that it is about the same speed as a slow baseball pitch, to put into perspective. And it could hurt you, but not bad. It won't break a bone. So it was kind of what I expected, but a little bit more, because it's obviously more powerful than a Nerf gun. And in order to make it shoot, I took a can of hairspray and I sprayed it into the hole here. And then after I did that, I would put a barbecue lighter and light it, and that would light up the entire thing and create an explosion inside of it, which would then shoot the potato out of the cannon. And so yeah, that's my project.